Okay, over the river and through the woods. Here we go. So, does the table describe a function? Explain your reasoning. So, there are a couple of different ways that we could look at it. We can look at we can look at all the x values. Do any of them repeat themselves? We could also draw this 0, 1, and then 1, 2, and then 2, 3, and then negative 1, 2, and negative 2, 3. And if I was to draw vertical lines, there would not be a vertical line that went through those. So let's zoop, 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 zoop. It only goes through one at a time. So you have a function. Okay. Each input has one and only one output. Okay. Grandmother's house we go. So Little Red Riding Hood is traveling to Grandma's house to bring her cookies and tea. However, Little Red Riding Hood often gets distracted on her way to Grandma's house. So what we're going to do on this next part right here is that we're going to select one of the graphs that could be her journey and describe Red's journey to Grandmother's house. So let's look at each one of these graphs. The first thing we have to look at is the time. If you notice on the bottom of these, on the x-axis, every single one of them is time. And then over here on every single one of them, it's distance from home. So this right here is distance, or is home at the origin. Well, actually, I lie. This is home right here. All the way across the x-axis, that is home. Okay, let's talk about this. So if we notice on this very first one, she doesn't leave at 0 time. So she waited just a little bit. Okay, so she walked. Oh, then she either dropped something or something. She ran back real quick, got whatever that thing was, and kept on running to Grandma's house. So yeah, that could happen. Then graph B. So she waited a little while. She ran. I don't know. Did she run to Grandma's house and then run back home? I don't know. That could have been it. On this one, I already drew a little bit there. So from here to here, she waited a long time and then all of a sudden she went to Grandma's house. I can see that happening. Somebody's going to say, but I thought she got distracted. Yeah, this whole time right here, she got distracted. Now this one, she got a little bit of distraction there. Right here, she goes to Grandma's, or she starts on Grandma to go to Grandma's, but somehow she was here and here at the exact same time. Can we ever be in two spots at the exact same time? Some distance from home, okay? This would never happen, okay? So this would not happen. That's not going to be. So this one, she waited a little bit and then she left for Grandma's house. And then somehow she went back in time. I don't think we can go back in time. So that is going to be no. Look at this one. She waited a little while. Then she went on her way. And well, maybe she was tired and needed to sit down for a little while. Okay, I can see that happening. So she stayed where she was. And then, or maybe she was picking some flowers. And then she went to Grandma's house. So all of those basically, except for D and E, could happen. Each one of those other ones could happen. Now, which one of them is not a function? So if I was to draw horizontal lines, those are horrible horizontal lines. Which one of these would be functions? And which would not be a function? Okay, so to pass the vertical line test, as I look at this, that one passes the vertical line test. This one passes the vertical line test. C passes the vertical line test. Well, this one, that has a vertical line. So that's not going to pass the vertical line test. So that is not a function. This one right here, it's going to go through 2 points at the same time. So that is not going to pass. And then F passes the vertical line test. So each one of, or sorry, A, B, C, and F are all functions. Okay, so let's look at this one. You and your friends are rock climbing a vertical cliff. Okay, so I have a vertical cliff right here. It says it's 108 feet high or tall along a beach. Okay. You have been climbing for a while and are currently 36 feet above the beach. So right here, there's a ledge at 36 feet. That's how far I've gotten. You stop on the ledge to have a snack, and then you climb again, and you climb at about 12 feet in height each hour. Okay, 12 feet per hour. So consider the height from where you begin climbing after your break. So we're starting at 36. Okay, so we're starting at 36 and we're going at 12 feet per hour. Change my color. Define the variables for the changing quantities and explain the independent and dependent. So time, guys, most of the time, time in hours, that is going to be my independent. Okay, then height, so my height and feet is my dependent. Depending on how much time has gone by is how high we've gotten. Okay, so we're going to sketch the graph. Now, it says after we've taken the break. So if I have a graph like this, down here is going to be my time. Over here is going to be my height. And this is in feet, and this is in hours. Okay, so I'm starting at 36 feet. Okay, I'm starting at 36 feet. Then it says I'm going at a steady rate at 12, oops, I didn't mean to write H, feet per hour until I get to 108 feet. Okay, I didn't put an arrow on the end because you're going to stop at 108 feet. You're not going to go past 108 feet because the cliff is only 108 feet tall. Okay, which quantities are changing? Okay, the changing quantities, the time and the height. And I'll change colors. Okay, which quantities remain constant? The constant is the 12 feet per hour. Okay, so we're going to write an equation. So in the past, we've done y equals mx plus b, where m, or I should do this, where this is my dependent variable, this is my slope, this is my independent, and then this is my y-intercept. So on this one, instead of my independent or my dependent being y, it's h. So that means we're going to have h equals my slope, 12 feet per hour. So 12. Instead of x, my independent is time. It's t. Plus, where did I start off at? At 36 feet. Okay. So I already went ahead and wrote this on here. Okay, so we started at 36 feet. I'm going to pick a different color. Okay, so right here is 35. So we're going to start right above 35. And then my slope is 12 or 12 over 1. So I'm going to go up 12. I'm going to go to the right 1. So I'm starting at 36. Well, 36 plus 12 is going to get me 48. Well, right here, this is 45. So just up here and then over 1. So this is the point 148. Then I'm going to add 12 more to 48, and that's 60. So I'm going to go up to 60. So I come up to 60 and I go over 1. So that's the point 260. Then I add 12 more, that's 72. So I'm going to come up here to about 72 and go over 1. So that'll get me 372. Then 72 plus 12 is 84. So I'm going to come up here, almost here, and then go over here. So that's 484. So I add 12 more, that's going to get me 96. So I'm going to come up here and go over 1. So that's 596. And I didn't quite put enough numbers on here, but that's okay. I'm going to go up 12 more, and that'll get me to my 108. So right here is 105, right here is 110. So I'm going to come across and go over about here. So that's 6108. Now, why didn't I go past 108? Because the cliff is only 108 feet tall. So then I'm going to draw a line segment that kind of connects my points. I'm a little off. That's okay, I'll make my dot closer over there. There we go. Awesome. So I really don't necessarily need all these extra little points. Is it going to hurt my graph to have them? No. But there you go. So we're going to state the domain and range. Okay. Now, the domain, the range. Okay. For the domain, we started at 0 time. We ended at 6. Now, we haven't really talked about this yet, but I want to tell you the t is in between there. The time is in between there. The reason that this is not just points, that this is an actual line, it's continuous, is because time is continuous. You have seconds, you have milliseconds. So it's every number that's in between 0 and 6. So how am I going to write that? Less than or equal to and less than or equal to. That will stand for the fact that it's every single number that's between 0 and 6 for time. The same thing is with the range, because with height you have millimeters, you have even smaller than that, which I don't know what they are. But we start at 36 feet. We're ending at 108 feet. The height is in between there. And so we write less than or equal to, because 36 is less than 108. That's why they're less than instead of greater thans. Okay. Oh, and the other thing I forgot is, because we're talking about domain, we're supposed to have braces for a set. Does this situation represent a function? Yes, it does. Because you can't be in two places at the same time. Okay, now some of you said that if it's not linear, it's not a function. Okay, so you have to be careful with saying that. Okay, all functions, are they linear? Are all functions linear? Those are two different situations. So we're going to talk about that. When you graph the input and the output values, that means the x's and the y's of some functions, the graphs form a straight line. A function whose graph is a straight line is called a linear function. So a function whose graph is a straight line is called a linear function. Important to know that. Consider what you know about linear relationships. Is every line a linear function? Well, if I drew this, would that be a function? If I drew this, would that be a function? Okay. Now, if I drew this, would this be a function? Okay, so all of those are functions so far. So let's try one more. I'm actually going to change. Nope, I'm going to leave the color the same. What if I drew this? Is that a function? It is not a function. Okay, so no, because a horizontal, try that again. I don't know why I wrote horizontal. Sorry about that. A vertical line is not a function. Okay. So then it says, is every linear function also a proportional relationship? So I'm gonna change the color for that one. I'm gonna bring that one here. So is every linear function also proportional? That means do all lines go through the origin? Do all lines, that was a horrible line, sorry about that. Well, let's look at it. Does this one go through the origin? No. Okay, and then the last part. Okay, so is every proportional relationship, so these kind right here, are they a linear function? Yes. And somebody's going to say, what about this right here? But that's not proportional. Okay, awesome. So the next one, describe how the independent and dependent values change in linear functions. Okay. Oops. There is a constant ratio. There's a constant ratio between the dependent. Remember the y goes on top, the dependent. I'm going to sneeze. And independent values in linear functions. Okay. So write the linear function with m as the slope. So we're going to write it as y equals mx plus b. So it's the same thing that we've been doing. Okay? Same exact thing. So here we go. We're going to write, we just have to find the slope and we have to find the y-intercept. So Lynn is tracking the progress of a plant. Sorry, her plant's growth. Today the plant is 5 centimeters high. So that is important information right there. The plant grows at 1.5 centimeters per day. So that's important information right there. Write an equation that relates h to the height and d after the days. So h, oops, I wanted different color maybe. So instead of y equals mx plus b, we want this to be h and we want this to be d. So what's the slope? Which one of those two is the slope? Remember that it's something per something. So this is the one that says per. So 1.5 is my slope. So 1.5. This is where it started from. So that's what goes there. Okay. Initially. So starting out. So at week 0, how much money does she have? Each week she withdraws. That means she takes out money from her account. So here we go. We've got to figure this out. From here to here, notice the amount gets smaller, and it gets smaller by $75. This goes down by $75. Goes down by $75. Well, what minus $75 will get $8 or $825? Hopefully you know that that's 900. So this is our initial value. Okay, so that is my y-intercept. So that's the plus 900 part. What does it go up or down by? Negative 75. So it goes down by 75. Now, it's talking about weeks this time, and it's talking about her balance. Okay, let's look at this one. We're doing the same thing. Okay, it's dealing with miles and T for cost. So we have to find the slope. Okay, so how much are these going up by? So from 16 to 20, that's up by 4, and there's halfway in between, so that's 18. So that went up by 2. And this down here went over by 20. So my slope on this is 2 over 20, which is 1 over 10. Where did it start? It started right there. So T equals either 1 over 10 T plus 16, or you could have written it as 0.10 T plus 16. Okay, so this next one, oh, this one's simple, Simon. Look at this. Write an equation that relates y, the dependent, x, the independent, if the slope is this and the y-intercept. They already give it to you. 2/3 minus 7, or 2/3 x, sorry. Okay, so let's go to this. Increasing and decreasing are constant. We've actually already talked about this before, so hopefully this will be pretty easy for you. It says Saturday morning, Erica walks for 30 minutes at a steady rate. So she walked for 30 minutes, steady rate, from her house to a park 3 miles away. When she arrived, she played basketball for an hour, and she caught a ride home with Kendall. They traveled at a constant speed to the park, to Erica's house, and arrived in 12 minutes. Okay, so what are the two things going on here? The time and the distance. So T equals time, and we're talking hours. How do I know it's hours? Or sorry, not hours. How would I know that's hours? Because it's not. It says minutes, doesn't it? So this is in minutes. And then distance, doesn't it say miles? So we're talking about distance in miles. So we're going to sketch a graph. Okay, so this is time, and this is distance, and this is in miles, and this is in hours. So she started at home. She walked at a steady pace for 30 minutes. Oops, that was horrible. Oops, I meant this, not this. Okay, so she walked at a steady rate, and then she stayed still for a little while. Well, she stayed still for longer than that. And then she caught a ride home, which is much faster than walking. Okay, so it should look similar to that maybe. Determine the rate at which she walked to the park and the rate at which she and Kendall drove home. So it would be distance, it would be the change in distance over the change in time. So it took her, or it was 3 miles she went from 0 to 3 miles. How come I can do it this way? Because didn't she start at home? So she started at 0, 0, it's proportional. And it took her 30 minutes to do that. So that would be 0.10 or 1 over 10. Okay, and that would be miles per hour. But then she also was traveling 3 miles, but it only took her 12 minutes to get home. It didn't take her 30 minutes to get home. So that's going to be 1/4, which is 0.25 miles. Why did I put miles per hour? Wouldn't that be miles per minute? Because this is in minutes, it's not in hours. Okay, so now let's look at this. So the domain with this. So walking to the park. Where did she start from? She started at 0. And remember, domain is talking about time. So how long did it take her to get there? It took her 30 minutes to get there. Okay, so as we talked about before, that's like this. And we're going to be using time. Okay, she was at 30 minutes. And she went an hour. So 30 plus 60 is 90. And then from 90, she adds 12 minutes to get home, so that's 102. Now the range for this, range is how far away she went. So in the first 30 minutes, she started at home and she got to 3 miles away. So that means my distance, oops. Okay. Now, she stayed at 3 while she was there. Then she went 3 back home. Okay, so it says write an equation that can be used to model this. So D and T, the distance from home as she walked to the park. Well, we said that that was 10 miles per minute. So, and we started at home. So we started at 0, 0, so there's no adding of anything. Now, we want to do Erica's distance. Oh, sorry. Oh, going from home while she was playing basketball. Her distance from home was 3 miles. And then from home as she rode home from the park. Well, she started at 3 and she went towards the house. And if you remember, she went at 0.25 miles per minute. Okay. Describe what happens to Erica's distance from home as, in each part of her morning as time increases. So as the time increased, as she got, as it got, as the time got further and further away from 0, what happened? Her distance increased. Is that how you spell that? No. I should have put her. Distance increased from home. Her distance was constant. It didn't change. I can't spell. Constant. Okay? And then on her way home, her distance decreased. Okay? So you can describe a function by analyzing the values of the function. When both values of the function, increase together, you have what is called an increasing function. When the y value of the function does not change or remains constant, it is called a constant function. When the dependent variable decreases, so when the y decreases as the x increases, you have a decreasing function. So it goes like this. So we're going to graph this. So as she started at home, I went up by 6s, by the way, on the bottom, and I went up by 3rds. So she started here. And at 30 minutes, she was 3 miles from home. So I'm going to connect the dots. Then for an hour, so that means 30 plus 60 is 90, she played basketball. So and then 12 minutes it took her to get home. So 90 plus 12, 102. And there you have it. Consider the graph of Erica's morning. What are the domain and ranges for Erica's morning in this problem? Okay, so didn't we just do that? And her range, we already did that. But we want to come down here and talk about this. Behavior means, is it increasing or decreasing? We talked about it. Walking to the park, she increased. She stayed constant while she was at the park. On her ride home, it was decreasing. Okay, so the equation here was, oh, we didn't use y, did we? Okay, so it would be d equals 0.1 t. This was d equals 3. This was 0.25, or it said 0 plus 3. Okay, the domain here, we started at 0 and we went to 30 minutes. Then from 30 minutes, we went to 90 minutes. And at 90 minutes, we went to 102 minutes. Okay. So what we're going to do on this graph is we're going to talk about the increasing, decreasing, and constant. So I'm going to do different colors. So I'm going to go, oh, you know what? I'm not going to do it that way. I'm going to actually highlight. So I'm going to highlight the increasing as pink. So the pink would be going like this and like this. Those are the increasing. Those are the increasing with positive slopes. Okay, the intervals of decrease. That means it's going down, or the y values are getting smaller as the x values are getting bigger. Okay, so those are negative slopes. And then the constant slope, I'm going to do red. The constant slope is when slope is 0. And I already answered number 10. Okay, I hope that helped.